Hey guys, Mr. Betts here. We're going to look at a couple examples that all use the same series and partial sum of the series. So I want to talk about the series itself first, and then we'll look into the questions that we're going to answer. So first of all, we have a series that's defined with the sigma notation here. And so remember, that just means that we can plug in consecutive values of n to get the terms in the series. So I want to do that real quick and just get an idea of what's going on with this series. So if n equals 1, we're going to have 2 on top. On the bottom, we're going to have 1 squared plus 3 plus 1. So 1 3, 1 plus 3 plus 2, which is 6. So the first term is going to be 1/3. The second term, we're going to have 2 over, now we're going to have 4 plus 6 plus 2 is 12. So that's going to be plus 1/6. And then we plug in 3, we get 9 plus 9 is 18, plus 2 is 20. So we get 2 over 20 or 1/10, and so on. We are also given in this problem a formula for S sub n that works for this particular sum. You don't have to know how you would get that partial sum. It is one thing that you could just get by kind of trial and error, or looking at partial sums and looking for a pattern. You can also do it more analytically using algebra, but you don't need to worry about that. So it can be shown that this is the partial sum. So for example, the third partial sum is going to be 3 over 5. Now we can confirm that if we add 1/3 plus 1/6 plus 1/10, we would need to get a common denominator there, which would be 30, it looks like. So we could do 10 over 30 plus 5 over 30 plus 3 over 30 is going to give us 18 over 30, which reduces to 3/5. So this partial sum formula will give us the sum of the first however many terms we want, and it's a very quick formula to use. So to the problem here, the first question is asking for us to find the 10th term in the series, but we want to do it in two different ways. Part A is going to be the easy way. So part A, we want to find the 10th term in the series using the series definition, using this right here. And essentially what that means is plug 10 in for n there. So to do that, I'm going to call this a sub 10. We're just going to put 10 in. So we get 2 over 100 plus 30 plus 2, which for comparison with part B, because we're going to find the same thing a different way, I want to simplify this here. So we're going to get 2 over 132, which reduces to 1 over 66. Okay. So the other way we want to do it is by using the partial sum formula. Now, I want to remind you that if we find the 10th partial sum, that's going to be 10 over 12, which is 5/6. That just tells us what we get if we add the first 10 terms together. If we want to know specifically what is the 10th term, we need to take the first 10 terms and then subtract the first 9 terms. So we also need to know what the 9th partial sum is, and that's going to be 9 over 11. So knowing what the sum of the first 10 terms is and the sum of the first 9 terms is, then we can find the 10th term by taking the first 10 terms and subtracting the first 9 terms, which is going to be 5/6 minus 9/11. Getting a common denominator, we're going to have 55 over 66 minus 54 over 66, which is 1 over 66. So the point here is basically to show you that using the sigma notation here or using a partial sum formula here, we can answer the same question in different ways or using different pieces of information, and we need to be able to do it both ways. So a problem might only give us one of the two, and if we have to answer the question just given one of the two, then obviously we're restricted to what's given to us. The other thing we want to do here is find the value of the infinite sum. So what happens when we actually add infinitely many terms together in this series? Well, remember, to do that, we're going to look at the limit of the partial sums. So what happens as n gets really big to those partial sums? So as we add more and more and more terms together, what happens to that sum? Well, This sigma notation here, this doesn't actually come into play at all. What's important for finding an infinite sum is the partial sums. So we're going to look at the limit as n approaches infinity of n over n plus 2. And remember, we're looking at relative rates of growth. So on top, the n is going to dominate because it's the only thing there. On the bottom, the n is going to dominate. So this is going to behave like the limit as n approaches infinity of n over n, which is just 1. So as we add more and more and more terms together, we're going to get a sum that's getting closer and closer and closer to 1. I do want to emphasize here, it's never actually going to equal 1. We can never actually add infinitely many terms together, but the sum is going to get really, 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 really close to 1.